Testing. Testing. Good. All right, welcome back from the weekend. Today we got a little GitHub repo, little project to start off the week called Bark. That's actually but Bark is a firmware-based text audio model device. Bark can generate highly realistic as well as other audio, including background noise. The model can also nonverbal communication. Trying to support the research, we're providing access to model check. So this is actually similar to another product that we had on this called 11 Labs is similar type of thing, basically for voice cloning, right? Where you type in text and it speak model. There's a bunch of these that are popping up and all the same. But this one has a couple unique fact that you add these non-speak sounds. Sound is choppy. Sure, that'll be a little better. That isn't better. No. Compressor. Close. What about now? Is it better? Still choppy? What about now? Is it better? Still choppy? Yeah, so I had a noise gate. So if you're into streaming, you might understand what this is. But basically, there's a noise gate which turns the microphone off unless there's a certain volume that's reached. And the reason you add noise gates is so background sounds don't get kind of filtered in. So turned off the gate. All right. So back to this, we got non-speech sounds. We got music. You can add little music emojis. Voice cloning, capability to clone full voices. We limit the audio history prompts to a limited set of Suno-provided fully synthetic options to choose from. To mitigate misuse of this technology, okay. Provide certain speaker prompts. Cloning official code and model weights. Alrighty, so what do I want to do? Laughs. Let's try all of these. Sigh. What about clear throat? And let's say man. Clear throat. Then we're going to say testing. Testing. Laughs. Testing. Testing. And then welcome to another repo stream. I'm going to submit that. So this isn't running on our computer. This is running on Hugging Face on an A10G. So here you can see it says Q 6 out of 6, and what that means is that there's people in front of us, some other random people on the internet that are also using this, and you have to wait in line to get your result. But if we wanted to, we could take this and duplicate it and then run it on our own Hugging Face dollar, I guess, and then we could get it instantly. But I'm more interested in trying to get this to run locally and check out this code. So let's see exactly what they got here. Alright, so there's no requirements.txt here, but if you do notice, they do have a 2ML here. So this is a new kind of environment management tool. I've seen it kind of pop up a little bit more, but I don't know, I'm honestly not a huge fan, but we'll see. Let's see. Let's ask our good old friend, ChatGPT. How should I set up a .2ml repo in my Linux Conda environment? Conda Python environment. You gotta make sure to put the word Python in there, that's the key word. Okay, I mean, I already have Conda. I didn't need to have that, create a new Conda environment. I mean, I already have that. I guess we can do that. Let's make a new Conda environment. Dev clear. Let's come here and clone this repo. So now we have the need a pip install 2ml. Okay. So first of all, let's conda create dash name. We're going to call it bark. All right. Conda activate bark. All right, so you can see now that we are in the bark environment. Let's pip install 2ml. Okay. This is kind of weird. This is not what I want. I want to install the Python dependencies in the 2ml file. I want to install the Python dependencies in the 2ml file. Now we need another poetry package manager. Dude, what? I want this fucking garbage. What is this garbage? Let's do this instead. Let's open up a VS Code terminal. And let's go into this. Let's copy this right here. Go into our terminal, then we'll do a pip install, and then we'll put all those there. You need to copy everything here. Go like this. Remove the space. Come back here. Pip install. Now it's installing. Don't save. Okay, so if there is a tool.poetry, then yeah, tools.setuptools, tools.black. So I don't see a tools.poetry here, but I do see a tools.setuptools. It's probably what it wants us to do. Let's see if that actually does something. Is it still installing? Let's close out that one. Okay, so Python setup.py install. Alright, so we see there that when we ran the setup.py, it installed, but it basically installed all the stuff that we already installed, so that's fine. Yeah, that's GPT gave us this, it told us to install poetry, which actually doesn't seem like the right thing to do, but I don't know. I don't know why people want to change the requirements.txt or conda environments. I don't think we need another Python management tool, but it seems like we mostly have it installed here. So let's use this little example here and see if we have everything there. So start up a little terminal here. Actually, let me clear so you guys can see it. We're going to start up Python. We're going to import from Bark, import sample rate. And what else do we want here? Generate audio preload models. Okay. Okay. What is the sample rate? So sample rate, my guess is 44,000. No, 24,000. So it's a smaller sample rate. So sample rate is basically the resolution at which you encode an audio waveform. And actually, why don't we ask good old ChatGPT. ChatGPT is going to have a good idea, but tell me about audio sample rate. What is the standard in the music industry, and what is a low and high? Right, and this is one thing that I noticed too when I was using 11 Labs and I was kind of messing with some audio stuff months ago, is that you can actually reduce the sample rate and the quality is still pretty good. So yeah, it's kind of one of those things where, yeah, 44,000 is kind of the number I have in my head, and that's audio CD quality. 22,000. Oh, okay, so the human hearing is 20,000. So, okay, that makes a lot of sense now. Basically, as a human, you're maybe going to perceptually be able to tell between 20,000 and 10,000, but anything above 20,000 is probably too much. 48,000 is used in video production and broadcasting. 88,000, 96,000, and 192,000 are used for high-resolution audio, so 192 seems like the highest number I've seen. And then the lowest numbers are going to be 8,000 or 16,000. How to determine the hardware requirement if one wants to run these models locally. So that's what we're going to do right here. We're going to run this preload models here. So you can see here it's 5 gigs. Right, so we'll see if we can actually fit it on the NVIDIA card on this machine. But we can actually just also go into this function here. So let's go here into the fake classifier, I guess. Bark. Let's search in here, preload models. Here we go. Here's the preload models function. Okay, they have use GPU, use small. So this is a small model, and then they have, so they seems like they have a couple different sizes, which is good to see. If we go to this load model function here, course, fine, CUDA device, get checkpoint path, load encoded model, 24 kilohertz. Yeah, CUDA out of memory, so try to allocate 40 megabytes. So we're gonna have to do this. And we're gonna have to say preload models text use small equals true. Let's try that one. So this one's gonna be smaller. You see how the previous one was 5 gigabytes, and this one here is 2 gigabytes. So the small model is 2 gigs. That should be able to fit in our GPU, I think. And then here they're loading a different model called coarse, and then a different model called fine, and then a codec model. So there's actually 4 different models here. You have text model, coarse model, fine model, and codec model. Also getting, let's use the small for all of these. So let's say preload text use small equals true, coarse use small equals true, and fine use small equals true, and yeah, we'll do that. So all I'm seeing here, right, is what I'm really doing is like all of these, you see how the default value for these quarks here is all false, which means that by default it uses the big models, so I don't have a ton of GPU memory on this, so I'm just using the very small models. Yeah, that's a lot of weights. It's 1 gig of weights. Another gig of weights. So we can actually go to my GPU here and you'll see it load up the model. So you see, there you go. Actually, that fit quite well. So the small version of all these models fit inside my GPU card. So there's 3 models or 4 models here, right? And you can see that it downloaded, previously the big model is like 5 gigs. With one of them being small, it ends up being about 2 gigs. And then with all 3 of them using the small one, so small text, small coarse, and small fine, you end up getting 1.25 gigs. And when it loads into the GPU, you can see it here, it's only using 3 gigs out of my 8 gigs. So yeah, RW, the hardware requirement for this is 3 gigs of GPU memory if you want to use the smallest models. But the smallest models are also going to be not as good, right? They're probably going to be a little bit shittier. So take that with a grain of salt. Let's go back to the example here and see what they have to say. So we were able to preload the models. Now we have to provide a text prompt. Okay, so let's go ahead and let's say audio array equals generate audio. And what's a text prompt? Let's say hello world. Hello world is kind of one of the first things you learn in programming is printing that. So, all right, so you see it's doing something here. 100 out of 100, 12 out of 12. Let's see what this audio array is. Audio array is a NumPy float. So what is the type of that? It's a, or shape, sorry. So it's a 112 by 000, right? And we know the sample rate. So actually what you can do here is you can say audio array.shape 0 divided by sample rate, and that'll tell you how long the audio is. So this is 4.6 seconds of audio. And then the type of audio array is a numpy nd array, I think .dtype. It's a float 32. So here's a question I have for ChatGPT. Can audio arrays be stored in data types that are lower precision than float 32? Right, because theoretically, if we could fit this in a float 16, we could always we could half the size of this, right? But okay, so actually, look at this, right? 8-bit integer. So images are like this too, right? So images, normally when you're storing them on your computer, they're not stored in float 32s or float 16s, they're stored in int 8s, right? Uint 8s, there's 256 possible values. So it actually seems like audio, you can do the same thing. Right. Okay. That's kind of cool, right? It's kind of cool that both audio and images, right? They're both modalities of the real world. They both represent, in one case, light information, and then in the other case, sound information. But the fact that both of those can be compressed into a 256 big little bucket is kind of interesting. That 256 is some magic number there that it seems to be pretty good enough for both of them. So it's kind of cool. I love it when the universe kind of has these coincidences like that. All right, so we have our audio and play text in notebook. I think in order to play this in this isn't going to work here, but let's see. Yeah, there's no audio. We need to download a different library probably in order to have it output inside the Python terminal. How do I play out a 8-bit quantization. 8-bit quantization more refers to taking the model parameters themselves and turning them into, or storing them as 8-bit numbers. But I'm more referring to the fact that raw images and raw audio can both be stored in 8-bit format, right? So you can think of that as 8-bit quantization for the actual data itself. Play out a Python or a NumPy float 32 audio array to my system from Python. Sound device library. I think this is the one we were using for the speech-to-speech project that we did. Do we even have it? Import sound device as SD? No. We do not have it here. Okay. That's fine. Let's close that. Yeah. Sorry, Kalina. It will affect the performance of the model to have a lower quality or lower precision data type. So quantized models always generally, I don't know if generally, but always, I don't know if always either, but quantized models will perform worse than the full precision model. Okay. So let's look a little bit more here. Generate text semantic. Generate semantic tokens from text. Okay, so we see that they're taking the text and then they're turning it into tokens. So much like an LLM doesn't operate in raw text, it seems like their audio, text to audio here, doesn't operate in raw text either. So it converts, it's probably using a generic transformers. Where is the tokenizer? Is instance. Here we go. Tokenizer equals model container tokenizer, load model. So load model is creating a dictionary called models, and inside that dictionary it's load model F right here. It's adding a tokenizer to this model. So where is the tokenizer? Here you go. Here's the tokenizer. So the tokenizer they're using is a BERT tokenizer. So BERT is fairly popular. I feel like BERT is a little bit old at this point. There are better tokenizers than BERT, I'm pretty sure. BERT base multilingual cased. So cased is interesting. That means that the capital letters and lowercase letters are different. So you should get different tokens for a word with a capital letter and a word with a lowercase letter, which means that when you pronounce the word, it's going to sound different. So actually, let's see. This is done, so actually let's generate this audio right here. So this is the audio that we generated for the Hugging Face space. So if we hit play here.
Testing. 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 Welcome to another UFO stream.
It's like a British voice. Let's make it a little bit louder. I don't know if you guys heard that at all. All right, let's try it again.
Testing. 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 Welcome to another UFO stream.
I really like the way it pronounced the testing with the 4 I's. Like, that was really good. Yeah. It said testing. Like, that's impressive. So let's see, do you guys want to see this? Let's see how good it is at multilingual here. Let's say man, and then let's say hola, me llamo. What do you say to lo que quiero? So this is just kind of like a nonsense sentence, but it's in a couple different languages here. They do have different speakers, so maybe there is a specific language for the speaker, right? They say multilingual, but I don't think it's multilingual within the same prompt. It's probably multilingual in the fact that there's multiple pre-trained speakers. Okay, so we were looking at the tokenizer. BERT case multilingual tokenizer, it returns the model and the tokenizer here. Load model, use small. Load codec model. Okay, so this is the actual model code right here. Alright, so inside Bark, inside, okay, here we go, here's the model. So we have a layer normalization. Okay, they have a layer normalization with an optional bias because PyTorch does not have a bias. I wonder why they felt the need to do that. You know, I feel like most people would just use the kind of vanilla layer norm that comes with PyTorch, but why have a separate layer norm specifically for the bias, right? Like the reason the bias isn't there is because it doesn't really do much. Standard little transformer here. You got key query values. Got some self-attention. You got some dropout here, right? Flash attention, make GPU go burr, but support is only in PyTorch nightly. Okay, so they're kind of like implementing their own transformer here, which kind of seems a little bit unnecessary. And then here you have a little multi-layer perceptron, right? So this is going to be the head at the top. Yeah, this looks fine. This is better than some of the other code we've looked at for sure. I like what they're doing here with this config object, where they pass around this config object, and then that config object contains all the different things. There's a lot of, like, the way you pass around Python configs is like always kind of terrible. You know, like I generally like to pass it all as quarks and then do like a star quark kind of situation, so you can always know what the type is, and you can have type hinting and stuff like that. But the config object kind of design pattern is also pretty good. I like it. It makes it very clean. So you see here's the actual model. So you have layer norm, then your transformer self-attention transformer, then layer norm, and then a multi-layer perceptron. So this is like the actual transformer block here, right? And then here you have these are residual connections. So you see how basically you're concatenating the input X with the output of the attention block, and then you're concatenating the input X again with the output of the multi-layer perceptron. So what's going on there is it's the residual connections in the transformer. So if we go back to the transformer is all you need paper, right? This is the classic paper. Let's go here. But yeah, so you see here how the multi-head attention, right, and into this feed forward. The feed forward here is going to be the MLP. And you see how there's a skip connection that goes around that. So you see these skip connections? That's what this X equals X plus is. All right, we got, this is the actual config class, so I think that's what this is. So, you know, ideally they would do something like this, right? They would type hint it for you, so you know what it is. GPT config input vocab size. What is that? So the vocabulary size is going to be basically the tokenizer is going to output tokens, right? And the token dictionary has a limited size. There's only a limited amount of tokens. And actually, if you're doing multilingual, I think the dictionary is going to be much bigger, right? Because there's different languages have weird like sounds and weird tokens, so they probably have a much bigger dictionary than normal. So let's actually go BERT-based multilingual case. We can actually search for this on Hugging Face, and we can figure out answer this question. I'm curious as to whether the size of a multilingual tokenizer dictionary is bigger or normal than the tokenizer dictionary that you would use in a normal thing. So this is the actual tokenizer they're using. Pre-trained on the top 104 languages on Wikipedia, using a masked language modeling. So masked language modeling is basically very similar to next token prediction, except instead of basically having a sequence and then trying to predict the next thing in the sequence, you basically have a sequence, but part of it is masked out, right? So part of it is missing, and then you have to predict the middle part. So you end up with slightly different it's a slightly different problem, right? Trying to predict the next word when you have all the words leading up to it is going to result in a different kind of loss landscape. I don't know if that's the right word there, compared to having the entire sentence and then trying to predict the blank word in the middle. And I think the reason this mass language modeling is better for these multilingual models is that especially when you look at other human languages, I think there's kind of a much broader array of grammar structures. So English is like, I feel pretty straightforward. Like generally, like you kind of everything leads into itself. It's a very kind of linear language. But I think other languages have kind of more complicated grammar structures where like you might say the thing that you want to say here and then like flip it around. So instead of next token prediction, doing an MLM objective might help with that kind of multilingual stuff. But I'm also not like an NLP guy, so like I might just be bullshitting. If one of you guys is a NLP, maybe it's not a word dict, it's a sound model after all. Maybe the dict size is the number of sound bins. Yeah, so there's different models here, right? There's the first thing they're going to do is they're going to tokenize the text. So they're going to turn your text, right, our text right here, into a bunch of tokens. Actually, we can probably, here, I got an even better idea. Let's make a script here. Let's call it test.py. We're going to come here. We're going to copy their example. Put it here. Debug time, yeah, exactly. And we're going to put a breakpoint. And then we're going to run this. So we're going to debug this Python file. Okay, it's running. All right, and now we're going to step into it. So basically, I think it's this one here, step into, yeah. So first thing it does is it loads the model. Okay, we can kind of skip through all of these. Right there, it's loading the first model. That's what it's taking over, taking a second here. Or actually, wait up, we already fucked up because we need to use the small ones. Yeah, out of memory. It's fine, I get it, little computer, chill out. Let's make sure to load the small ones here. Oh, nope. Right here, course use small, fine use small, text use small, copy, paste, tab, multi-cursor. Change these to Control W, true. Alright, run this again. Alright, we actually don't want a breakpoint here. What we want is the breakpoint here. So let's hit play. It'll load the models. It's loading the models. All right, there we go. Now let's step into this generate audio. So text to semantics. So if you see here, if we hover over text, we have our text, which is the kind of generic, hello, my name is Suno and I like pizza. What is history prompt? History prompt is none, text temp. So this is a temperature for the text model. It's kind of interesting. Why would the text to semantic have a temperature to it? And then silent equals false. So silent is probably just logging. And if we skip over that, and now we get this. Now we have semantic tokens. So you see, tokenized. All right, now our semantic token is of type 592, and it's int64, and these are the tokens. So you see here, it has turned our text into basically a bunch of tokens, which are like indices in a dictionary, right? Your tokenizer has kind of like a dictionary, and It's unfortunate that the word dictionary also refers to a hash map in Python, but when I say dictionary here, I'm referring to kind of the dictionary that you would have like in your house, right? So what this is saying is that the first token in this text is word number 215, then word number 215. So actually, the first two things are the same token. So if we go back to our text, what are the first two things in this text? Space, space. Hello, my name is Suno. So probably 215 is a space, if I had to guess, in the dictionary. Right, but you can see here, you can scroll and like the biggest number will kind of roughly tell you how many tokens you have. So you see there's no number here. The biggest number is here is 9,741. So we know that our dictionary that is used here for this tokenizer probably isn't bigger than 9,700. So we actually go to the BERT multi-case. Tell me how big this is. Size. Holy shit, way bigger than that. 110,000. Damn. That doesn't seem right. That's a whole lot of fucking tokens. Right? Let's ask ChatGPT. Is there a significant difference in the size of dictionaries for text tokenizers that are English only and text tokenizers that are multilingual? Yes, there is typically a significant difference in the size of tokenizers for English only and those that are multilingual. English only are designed to handle only the English language, so blah blah blah. Can you give me examples for BERT and multilingual? BERT, I want the number. This is actually super interesting because I bet you there's probably information there, right? I bet you if you have a multilingual tokenizer, you have more possible different tokens, and then more tokens results in more unique sounds, and there's probably like some weird kind of transfer learning going on where like if you get really good at pronouncing Spanish words, you're probably getting a little bit better at pronouncing English words, right? And vice versa. So 110,000 tokens, we're getting roughly the same thing. So ChatGPT tells us 100 and what is it? 119,000 tokens, and then this is telling us 110,000 tokens, so I guess that's probably the size here. Okay, and then once you have these tokens, then you turn it into a waveform, and a waveform is basically just that, right? It's like an amplitude, a frequency at a sample rate, right? It's basically that represents audio. Audio is basically a pressure wave in air or any other medium. What happened to my audio? Oh no, is my audio not working? I don't know. Hopefully it's working. It sounds like it's kind of working. I have like a mirror that like shows it to me, but if it doesn't work, let me know. It sounds like I'm underwater. Yeah, I had to remove, so I had some like audio post-processing going on. I had basically like a noise gate. Semantic tokens are the tokens, so they're basically just the text turned into tokens. Right, so rather... So this audio is not really... What the hell are those indices? They're the tokens. They're the indices of the tokens, right? So this isn't a text to audio model. It's not going directly from text to audio. It's going from text to tokens and then from tokens to audio. Yeah, so the indices are the vectors. So whenever a tokenizer turns it into tokens, those tokens can be represented, rather than saying, hey, here is a 1024 dimensional vector that represents the token HAP. It's going to say, I want token number 654, right? So there's an implicit mapping there between the actual embedding vector that that token represents and then the actual token. BERT is actually doing that, right? So BERT is the one that's tokenizing it. It's just that people store the tokens as int64s rather than storing them as float32 embedding vectors. That's the whole point, right? Like if we actually go into this, let's go into this function here. Yeah, so you see? So here's the semantic tokens, which are the int64s, right? And then the coarse tokens will be float32s. See, so this is where it's actually turning the int64 tokens into float32 embedding vectors. So now these are vectors. Yeah, here you go. Or maybe not. These are still not vectors. These are still int64s. Yeah, I don't think this is... Let's see what this generate course is. Generate coarse audio codes from semantic tokens. Semantic tokens is what comes out of BERT, right? We actually go back to our test, back to generate audio, back to text to semantic, generate text semantic. Somewhere here is going to be the tokenizer call. Instance, normalize, history prompt. We don't have a history prompt. Model is none. Here you go. Tokenizer. Model container tokenizer. So here's the actual BERT. And then you're taking BERT and the text and you're converting it here. So here it is. Here's the actual call. Tokenizer.encode. So here's where the BERT is actually getting called. Right? This is BERT right here. Okay, so back to generation. Actually, where were we? Let's move this over here. Alright, so I don't know what this coarse and fine tokens is though, right? Like I'm not 100% sure what the fuck that is. So what is the difference between coarse and fine? So coarse audio codes from semantic tokens. Sliding window. History prompt. We don't have a history prompt, so fuck that. Okay, so here it's making a history. Load model. It's loading the coarse model. It's making sure to put it on the GPU or the CPU, depending on which one you have set. You see here the code book. So this code book is actually what converts the tokens to the embeddings. Right? Where's the code book? Let's search for code book here. Actually, the codebook size seems like it's a hard-coded all caps variable, so let's look at that. Codebook size, 1024. So I think that's the actual size of the embedding vector. KV cache, so this is actually the transformer coming in here. The key and the values, that's what the KV is. Log it, so now you see here's the actual model call. So the model will return to you raw logits. Logits just refers to the fact that it hasn't been fed through a activation function, right? and you take those logits. They roughly represent the probability of the token being, right, ultimately what you're doing here is kind of like classification, right? You're saying, hey, I have this number of possible tokens that it could be, and I'm going to get each of the logits for each of those represents roughly the probability that it is that one, and I'm going to find the one that is the highest probability. So here you can do top P, which is a slightly different type of way of picking the best logits. So you can see here, torch top K. It'll take those logits and it'll tell you, okay, this is the top probability one. Once you have the one that is the top probability, then you can convert it into audio tokens, and then they probably have a way to go from audio tokens into actual waveform. This should be fine. Generate coarse audio from semantic tokens, and then generate full audio from coarse audio. So they have actually, it's almost like a upscaling kind of thing. It seems like they basically have 3 steps here. They convert the text into semantic tokens, then they use the semantic tokens to convert it into coarse audio tokens, and then they use those coarse audio tokens and they kind of like upscale them into fine audio tokens. So 2 different models here, coarse and fine. So let's see if we can figure out what these coarse and fine models are. I assume that they might even be just the same exact model, just like 2 copies of the same model. Right, we see here that the fine is using the same codebook size. CUDA, clear CUDA cache. Let's see what their clear CUDA cache function looks like. Torch CUDA is available, torch CUDA empty cache, torch CUDA synchronize. We have a context lib, context manager. So this decorator here in Python is so that you can do something like this. You could say with inference mode has blah blah blah, right? So whenever you have this decorator here, it's basically going to be so that you can use it like this. Inference context, S3 bucket path. Okay, so S3 is Amazon storage. So in Amazon cloud services, the kind of abstraction for storing data and storing information and storing things is called S3. So here, this is telling me that they're training this on AWS, or at least they're storing things on AWS. Here is the actual paths. So HTTP, DL, Suno models, Bark models. Actually, we can go to this website here and we should be able to see all the other models that they have. No. Of course, there's not. Clean models. What does clean models do? Oh shit, look at that. So basically, if you load multiple different models at some point, it's going to make sure that you don't have any extra models sitting in your CUDA cache. That's a pretty good thing, right? If you have any kind of like system that has multiple models, right, sometimes you can end up in a situation where you have stale models that are just sitting there and you never actually garbage collected, so they have like a little function here to clear out all your CUDA memory and then garbage collect your Python so that you don't have stale stuff sitting around. And then this codec model might actually be the one that actually turns, let's see the codec. I think the codec is the one that turns the fine audio tokens into the actual waveform here. So in codec model operating on the raw waveform. So you need an encoder and a decoder. What is the input to this? Encode, given a tensor X rescaling. Each frame is a tuple codebook scale with codebook of shape BKT, and K is the number of codebooks. Decodes the given frames into a waveform. Okay, so you have an encoder and a decoder here, right? And I think a good way to show this, encoder-decoder neural network, right, is that what encoders and decoders are doing is they're compressing information, right? So they're taking, this is probably a good picture here. So in the image world, right, you can take an image, you have a bunch of convolutions, and it compresses it down into a smaller representation, right, which you can call an embedding. And then you have a decoder which takes that and basically turns it back into an image, right? So it takes that compressed representation, turns it back into an image. And the real benefit of this kind of encoder-decoder kind of design pattern, is that you can use a loss to say, hey, well, the thing that you encode should be the same as the thing that you decode, right? So I bet you what they did here is they trained this encoder they trained this encoder and this decoder by just giving it a shit ton of audio. So they just have a huge amount of audio, they try to encode it, and then they try to decode it, and then the decoded audio should match the encoded audio. And if you do that on a big enough database of audio, you're going to get a pretty good encoder and you're going to get a pretty good decoder, right? So then you can just take that decoder and then use it to decode the tokens that you're getting from the coarse and the fine part of the model. So I don't think they use this encoder at inference. I think the encoder is probably only used for training, and then what they're really interested in is the decoder. LM, is that a language model? See how they have they have a 24 kilohertz encoder and then a 48 kilohertz encoder. The fact that all of their examples are 24 kilohertz tells me that they tried 48 kilohertz and it wasn't actually that much better. This is the actual encoder here. So the encoder that they're using is called CNET. What is this? CNET. Let me look for this. CNET encoder model. Is this something they made themselves, or is this... here you go. Okay, this is the one. CNET. We propose a lightweight model for frequency bandwidth extension of speech signals, increasing the sampling frequency from 8 kilohertz to 16 kilohertz. The model architecture is based on CNET, Sound Enhancement Network, a wave-to-wave, fully convolutional model. Okay, so this is a 2021 paper that uses CNET. Let's see if we can find the original CNET paper. Actually, this one probably references it, so let's actually see. Let's scroll down to the references in this paper. And here you go, CNET, Multimodal Speech Enhancement Network. So this is the actual encoder-decoder that they're using here. So this is a 2020 paper from Google Research. And here it is, boom. There's your encoder and there's your decoder. So you can see some skip connections going through there. And generally in those kind of encoder decoders, like a unit, for example, the skip connections are very common. So you see here, okay, it's kind of cool. You know what I'm actually curious of? I wonder if some of the authors of this paper, Grimes, that artist Elon's ex-girl, says we can use her voice and get 50% of the profits. Or you can just make the audio and get 100% of the profits. You know, I don't think you need to give her your money, because you don't need to say that it's her, right? It's, will they? That's the question. At what point, if you don't ever use her name and you don't say that it's her, you know, like, you could make a song and if you don't ever mention anything that she has copyright over, then you're probably fine, right? Like, you can't copyright, like, sound. Yeah, I think they only have copyright on the actual, like, name of the artist, the name of the songs. You can't use the picture of Drake, but you could use Midjourney to generate a picture of a guy that kind of looks like Drake but isn't Drake, and then call him, like, Bob. It's not her voice, right? You could basically make a voice that is very similar to hers but isn't her voice, right? Like, I'm sure there's plenty of, like, women out there that have a voice that's very similar to Grimes and they can't sue Grimes, right? I think this is the future of, like, creative generation is not very understood, because it's like, it's going to get very easy to generate music and generate, like, for example, let's say Game of Thrones releases a new episode and you generate an anime version of it. Do they have copyright over that? Like, how different do you need to make your anime Game of Thrones before Game of Thrones is allowed to sue you? So I don't think copyright law accounts for the fact that you can basically make things that are kind of similar. And if they say, okay, well, this is illegal, this is too similar to the song, this is the song of Grimes, this is the song that you make, this is too similar, all right, we'll just make it a little bit less similar, and a little bit less similar. And at some point, it's going to be different enough that they can't sue you for copyright. And that distance is not even fully understood yet. So, I don't know. If I was making Grimes music, I would definitely not give her any money, because she's rich, and rich people are always hungry for more money, but the secret is that you don't have to give them your money. Okay. Right? Dude, fuck rich people. Alright, so here's what I wanted. I'm curious as to whether the people from Suno Labs, if any of them are these guys, right? So they're using the CNET, Sound Enhancement Network, which is kind of like a strange one, right? We're talking about a 2020 paper for encoding. So let's actually go here. Let's see. Greg Cusco, Keenan Freeberg, Martin Camacho, Alex Doe. Okay, it's not one of these guys. Let me see who actually is Suno. Foundation Models for Audio AI. That literally means jack shit. You're not going to be a foundation model company. Like, I don't understand these people. PhDs in physics, faculty at MIT. So if you want to know about a startup, there's a website that all the VCs use. You guys probably know it, but it's called Crunchbase. So you go into Crunchbase and you search for a company. Let's look for Suno AI. Suno.ai. They're not even on Crunchbase. That means they haven't raised any money. Here you go. When can you call a model foundational? There isn't a formal definition for foundation models, but to me, foundation models is more indicative of the scale, right? To me, foundational models is something like Meta's ESM2 protein model, or something like the segment anything model, or something like GPT's, the LLM that GPT is based on, right? I think you need to have a huge amount of data and a huge amount of compute in order to claim that your model is foundational, right? So I have a hard time believing that a 10-person company from Cambridge, Massachusetts spent $500,000 training an audio foundation model on a huge amount of audio data. They probably spent $1,000 training it, right? So like, is that really a foundational model, or is it just a specific audio model? Right? Did they go to Spotify and spend $1 million to get every single one of Spotify's audio and then train on that Spotify database? Probably not. So it's like there isn't a formal definition for foundational, but to me it's like the scale that's implied. Okay, so we were looking at this company, Suno AI. They've literally done nothing. So they haven't raised any money, which is good. You know, I don't think you need to raise money if you don't need it, but that's also indicative that, hey, if they didn't raise money, it's very unlikely that they had a huge amount of training budget, right? Let's see 10 similar companies. We got, this is not similar companies. Yeah, these are stealth. These guys like just have nothing here. It's kind of cool. About. We'd love to hear from you at hello@Sunny AI. So yeah, if any of you guys are interested in jobs, I'm sure these guys would be interested in finding people. So there you go. Message them. This channel is not sponsored in any way by Suno AI, but you know, we're looking at their code. They do seem to know what they're doing. Unit generator. So, okay, going back to the code, what were we looking at? We were looking at their encoder-decoder, which outputs into an audio waveform. The encoder and decoder that they're using is based on this 2020 paper by Google. And that 2020 paper by Google is based on a UNet, which is a model that is quite old at this point, but people have been kind of making it better and improving it and using it to inspire new things over time. Let's see what other things they have here on this SHA-net or CNET. So you can see here you have activation functions, so probably GELU versus RELU, right? That's a classic little hyperparameter that people love to tune. Norm, kernel size. So this is a convolution based. So this is important to realize, right, that there's different ways to treat audio as a modality, right? So some ways, one way that people treat audio is by making these spectrograms. So sometimes what people do is they'll turn audio into an image, right, like this. This is called a spectrogram. And when you turn an audio into an image, you can, actually, this is perfect. This is exactly the image I want. So here you go. Oh, let's open this image in a new tab. Yeah. So this is a raw audio waveform, right? I guess this is saying rice university, right? So you could have a convolutional neural net that convolves over the image of the spectrogram image. So you can think of it as basically you have a little convnet and it's taking the spectrogram image and it's basically convolving over the spectrogram image, right? Or you could have a convolution that actually is like a one-dimensional convolution, right? Where it's just only acting on the 2D audio, right? And it's convolving on the waveform itself, right? So that's probably what's going on here, right? And that actually comes from an even older paper called WaveNet. So yeah, this is what convolutions in audio space look like. This paper is borderline ancient at this point, I feel like. But basically every single one of these little dots down here is a sample, right? And in 22,000 or 22 kilohertz audio, there's going to be 22,000 samples per second of audio. So each of these blue dots is whatever, 1/22,000th of a second of audio. And then you have the dilated convolution there refers to the fact that it's skipping some, right? So this right here, dilation, how much to increase the dilation within each layer, that's what this means, right? So you see here, the first layer is dense, there's no dilation. The second layer has dilation 1, which means it skips every other neuron, right? The second layer here, so this is like there's multiple layers of this neural net, right? The second layer of the neural net here has a dilation of 2, which means it's now skipping more. You can see this dilation 4 skipping more. So the dilation base here is how much more you're dilating as you go up in the model. Whether to use true skip or simple convolutions as the skip connections. Okay, so some extra little magic here on the skip connections. And then LSTMs at the top. This is not, I don't like LSTMs. LSTMs are long, short-term memory. It's like a kind of an, I want to use the word ancient, but it's an old way of doing kind of sequence tasks where you have these like memory gates, right? Spotify will create their own AI music artist. Yeah, that's what I suspect. This is an LSTM model, right? So you have basically the input, and then you have this context coming from previous steps. And you can basically have a bunch of these blocks, and then there's also bidirectional LSTM. So LSTMs work in one directional, but then there's a bidirectional LSTM which works in both directions, and you can get more information that way. But I think this is one directional. And what else we got here? Final activation, blah, blah, blah. So you see the activation that they're using here, it's not even ReLU or GELU, it's just LU, which is slightly different. Let's see if we can actually get a plot of that bad boy. LU versus ReLU. Here you go. LU, ReLU, and GELU. So ReLUs are the ones that you're normally used to, which is 2 straight pieces. You have the flat piece here on everything below 0, and then you have a linear piece here on everything past 0. GELU is basically very similar, except you have this little area here right beneath 0 where you can have a little bit of signal leak through, right? You can have a little bit of a negative activation. And then LU is even more extreme in that you can have big negative activations, right? They're kind of capped at -1, so you're never going to have an activation that's more negative than -1, but you can have -1 activations. So that's the LU. Pad mode reflect, which is kind of interesting. So whenever you're doing convolutions, right, you want to go all the way to the edge, right? But what happens when you're at the edges of the image, right? Like, what do you fill in the missing part of your convolution with? So sometimes you can zero pad, and basically that means that you're just padding the image with a bunch of zeros, or here you're padding the audio waveform with a bunch of zeros. But sometimes padding with zeros kind of messes with the kind of model, and it kind of like, it makes it weird, right? Because it's such a weird thing to see just a bunch of zeros that it'll fuck with the model. So reflecting here is an interesting kind of padding strategy for audio. Maybe someone who's like an audio specialist can let us know about that. Here's a little test, okay? That's kind of cool. I would have just done this. I would have just put this right here, like that, and gotten rid of that. But Here you're creating random 24,000 samples, which is basically 1 second. You're encoding that, so you're taking that 1 second waveform, 1 second of audio, encoding it into a little vector here, latent vector. You're asserting that the vector is of this size, 128 by 75, right? Much like a convolutional network turns a 3-channel image into a possibly 256 channel image, right? The convolutional network takes the width and the height of the image and then makes it smaller and then makes the depth bigger, right? You can think of the audio as doing the same thing, right? It's turning 24,000 samples along kind of the time dimension and turning it into 75 samples or 128 and then making that deeper, right? So rather than being 1 deep, 24,000 long and then 1 deep, it's now 75 long and then 128 deep. So there's more semantic information there. And then this decoder is taking this and turning it back into audio or a waveform. And the size of this encoder and the size of the decoder should be about the same. So actually, I do like the way that they make this because you can use this encoder and this decoder yourself. So if you have any kind of audio project, let's say you want to have an audio classifier, or you want to do, I don't know, what other audio things can you do? Maybe like generating audio from images. I don't know, maybe you want to generate specific audio from images or something weird like that. You can use these encoders and these decoders here, right? You can encode audio and then use your encoded audio whenever you're training your weird image classifier and then decode it here. I don't know how much information, how much data they use to train these encoders and these decoders. That's the other thing, right? They claim it's a foundational model, but is it really a foundational model? Like what did they train this giant stuff on? You have the 24 kilohertz encoder, the 48 kilohertz encoder. You're loading a WAV here. WAV is an audio file. You have the sample rate. You feed it into the model. The model gives you the decoded. So this is just testing all the different encoders. I wonder, what did they train this on? I'm curious. Do they tell you what they trained this on? Voice presets, audio cloning. Oh, history prompt is the speaker. Why do they call it history prompt? They should have just called it speaker. CUDA 11.7, CUDA 12. On older GPUs or CPU, inference time is 10 to 100 times slower. Different from Val-E, the initial text prompt is embedded into high-level semantic tokens without the use of phonemes. Yeah, I think this maybe is the most interesting part of this paper here, is that I feel like in other audio generation, they break it into phonemes and then they just pronounce the phonemes. But here, they're turning it into tokens and then they have a custom model which turns those tokens into audio. So that seems like the biggest thing here, right? And they say here, therefore generalizes to arbitrary instructions beyond speech that occur in the training data, such as music lyrics, sound effects or other non-speech sounds. To enable the community to use Bark, we use the fantastic Encoder-decoder. What is this? I already started it, or started. High fidelity neural audio compression. Ah, okay. So this is the foundational model right here. So they say, hey, we're a foundation model company, right? Builds foundational audio AI. Their model isn't the foundational one. This is the foundation model right here. Right? And if we go here, what did they train this on? This is going to be the actual hardcore shit. This is where the actual foundation model work went into. Did they have the paper for this? What is the data set? That's what I'm looking for here. I'm looking for the data set that they trained this on. Data. We train Encodec on 24 kilohertz monophonic speech, noisy speech, blah, blah, blah. For speech, we use the clean speech segments from DNS Challenge 4 and Common Voice dataset. For general audio, we use Audio Set together with FSD 50K. And for music, we rely on Jamendo dataset. We further evaluate our models and music using a proprietary music dataset. Appendix A1. All right, so here we go. This is the actual stuff. So 10,000 hours of voice, about 3,000 hours of speech at 48 kilohertz, 48 kilohertz, 48 kilohertz. And you can always downsample, so you can always take 48 kilohertz audio, turn it into 22 kilohertz audio. And then 919 hours of Jamendo. So this right here is what they're actually using. So to encode their audio, they're using a Facebook model from 2022, and this foundational Facebook audio model is trained on roughly, let's say, 15,000 hours of mostly speech with a little bit of music. So that's really where the kind of base intelligence is coming from. Okay, so they use Nano GPT. They use Karpathy's. All right, that makes more sense. Okay, so why? We were looking at the model here, and we were like, why are they re-implementing a transformer, right? Like, what the fuck? Why are they doing that? Why wouldn't they just use the generic transformers that are available? And I think the reason why they want to do that is that they don't want to step on any toes, right? Like, it's not entirely clear who owns models at this point. So they rather be really careful and basically implement their own model so that nobody can say, hey, you're using our model, right? So that's why they're using Karpathy's. Encodec, which is actually where I think the actual intelligence of this model is coming from. This is the foundational model here, the Facebook model. Audio LM for related training and inference code. So what is Audio LM? This is a MIT license implementation of going. Oh, okay. So this is the actual like coarse fine token crap. So you go from the semantic tokens, which are coming out of BERT, convert it into coarse acoustic tokens, and then turn those coarse acoustic tokens into fine acoustic tokens. It's just a bunch of Russians, dude. It's all Russians. Okay, and then you have Val-E and Audio-LM. Yeah, so I mean, this is really just a bunch of glue, right? This is just a bunch of glue between Encodec and Audio-LM. Yeah, okay. All right, we're starting to piece together all the different parts here. So look at this. This tells a story to me, right? Where at the end of the day, this is a model that goes from text to speech, right? And you need a very, very good foundational audio model for this. And training a very, very good foundational audio is extremely expensive. And that is what they relied on Facebook for. So Facebook trained this encodec model, and this encodec model is what they're largely using. But the problem is that the encodec model released by Facebook is licensed under a non-commercial license. So technically, they can't create a business and sell a product that uses the encodec model. So the first thing that this startup needs to do, Suno AI, is to create an encoder that is competitive with encodec, that is their own, right? So they want to train their own encodec model. So that is why whenever you go on their website, they call themselves a foundational audio AIs, because really, I bet you what they're trying to do is they're trying to raise some money right now, and then they're going to use that money and then use all of that money to train a big encodec competitor. You see, which is very, actually this is very similar to what Stable Diffusion did, Stability AI. So Stability AI did the same thing, right? They used diffusion models, which were basically just an architecture that was out there, and then they trained their own foundational model on their own dime, right? I forget what that guy's name, Emad Mustak, that guy. He spent whatever, $5 million on AWS to train his own basically foundational image model, which is called Stable Diffusion. And these people are going to probably do the same thing. They're going to try to train their own foundational audio model that's going to be based on Facebook's encodec model, probably their own implementation of it so that they can separate themselves entirely from Facebook. And then they'll have a commercial license for their own model. So this is kind of interesting because to me it paints a new kind of path for AI startups, right? So if I was making an AI startup, what I would do is I would make a product like this that's basically just a bunch of glue, right? You create a product that just glues together a bunch of already existing foundational models and already existing AIs from other companies. But the problem is you don't have the right to sell that, so you just make demos and then you release the demo, right? You release the demo that is built using the publicly available foundation models. And then you use that demo to whip up investor hype, and then use that investor hype to raise a bunch of money, and then use all that money to train your own foundational model. Yeah, so the tricky part is that you can't sell anything until you train your foundational model. So Suno AI right now has to rely on this demo and eventually investor money in order to train something that they can actually sell, because right now they cannot sell this, right? If they try to sell any product with this thing, Facebook can sue them. But then there's also the reality that you can actually not your people aren't going to sue you, right? It's like it takes a long time to get sued, and like realistically, if you're small enough, no one's going to sue you. So you could maybe start being a little bit clandestine here and start selling this model and start getting a little bit of monthly users, a little bit of revenue, a little bit of daily active users, and then raise the money and then train your foundation model. But I think that's pretty risky. So pretty interesting stuff. Take screenshot. Nope. Let's open up a little flame shot. I have a little screenshot tool here. Resolve all. That's not what I want. Take screenshot. Give me this one here. I'm going to copy it. And we're going to go into Suno AI, and we are going to issues. We're going to make a new issue. And we're going to ask them a question here. So we're going to say, what will Suno AI foundation model be trained on? It seems like the biggest hurdle for Suno AI is the fact that the encoder-decoder is a non-commercial license from Facebook. My guess is the team wants to train their own foundational AI model from scratch. What data set will you use? For context, this is the data set according to the Facebook paper. So we'll see what they have to say about that, right? I'm curious what they will use. Because what big audio data sets are there available, right? Like, I do not know what that looks like. So let's ask ChatGPT. See. What large publicly available audio data sets exist? I currently have Common Voice 7.0, DNS Challenge 4, audio set, FSD 50K, and we won't give it the last one. We'll see if it actually knows. And let's give it some 10K hours. DNS Challenge 4, this is 2.5K hours. Audio set, this is 5K hours. And then FSD 50K is 100 hours. Can you find more audio data sets? All right, here are some more publicly available audio data sets you can explore. So LibriSpeech, 10,000 hours. Vox Celeb. Oh shit, here you go. This is exactly what you want. 7,000 hours of 12,000 celebrities. VCTK, 44 hours. Timid, 5 hours. That seems fucking worthless. 5 hours is like 5 hours is nothing, like compared to like 7,000 hours for Vox Celeb. Is this for commercial use too? Data set. Can I use this? Got Switchboard, 3,000 hours. Urban Sound, 8K. I'm going to interrupt it there. Is voice, or is Vox Celeb available for commercial use? Let's tell them. So we're giving them some recommendations here. CC by 4.0. What's the cool way to write CC by 4.0? So this actually seems like by far the best audio data set. Do they have text as well? No, I think it's probably not. Text. If you require text annotation, also consider using the LRS dataset. LRS dataset, 800 hours of audio with the accompanying text. But is it enough? Yeah, I don't know. Probably, right? Okay. Let's see insights here. You know, we love to check out the insights on this channel, so let's see what they got going on here. All right, so most of the code kind of came in here around April 10th, and then kind of from then on, it's kind of died out. Most of it is being pushed by this guy here, GK Kusko from Cambridge. Let's give this guy a little follow here. Slide tracker, LangChain. So this guy seems like he's in the. You see this? He's branched audio diffusion. He's branched LangChain. He's branched Bark. So this guy, or not branched Bark. He's like literally the contributor to Bark. So see, they got one guy there. What about this guy? Keenan Freyberg, also Cambridge, so this seems like a whole little MIT crowd that's coming on. This guy's a little bit more stealth. We don't really know what he's doing. And then McCamick, who came AC, what the fuck is this? Currently working on audio AI. Damn, dude, this guy's badass. Look at that. I studied computer science and math at Harvard, where I graduated at age 18. So this is like a prodigy child. I'm a little bit of a prodigy child, but not as badass as this guy. Like I went to Carnegie Mellon when I was 18, or when I was 16, so I skipped 2 grades, but this guy skipped fucking like 6 grades or something, right? If you graduate at the age 18, you're probably pretty nasty. So this guy's pretty smart. Let's give him a little follow there. He doesn't actually push a lot of code though. You know, like it's really not a lot of code. Maybe he just pushes to a lot of private repos. Sometimes people don't push. You don't see the contributions. Yeah. Okay. And yeah, and then I guess the rest is just people not. And then let's see commits. Yeah, so most of these commits coming in here, code frequency. You can see, right, they added the bulk of this repo, and then they just kind of add little things here, and then they mostly change some stuff around here. And then these are the dependencies, so obviously transformers, which is Hugging Face, they're definitely using it for the tokenization of the text, so that's largely what they're using transformers for. TQDM is a Python package that gives you these little loading bars, so if you like these little loading bars like this, then TQDM. Torch, obviously PyTorch, it's the machine learning framework. Tokenizers, I think that's another. Hugging Face, yeah, it's like basically Hugging Face, but specifically the tokenizer part. SciPy, kind of like a very old school machine learning library that people use because it still has all the basic parts, right? If you want to do like a support vector machine, linear regression, like it also has pretty good kind of like image stuff as well. Like SciPy is still used, even though it's quite old at this point. NumPy, of course, obviously for your vectorized stuff and storing arrays. Encodec, what is the state-of-the-art deep learning-based audio codec. This is the Facebook one. So this is the one they're like really desperate to get rid of, right? They really want to get rid of the dependency on this Facebook foundation audio model. FunC, fancy and practical functional tools. I've never heard of this. What is this? Merge collections. Okay, so, all right, let's see what's going on here. So basically, there's this whole like kind of like category of Python packages that are basically trying to Python. And what I mean by that is that Python is most well known because it's the kind of most easy language to learn, right? It's very syntactically clean. It's like it almost reads like English. And then people sometimes want to take it even more than that, and they come up with all these like little tricks that you can do. So like for example here, this func package adds the ability to create decorators with a decorator, right? So just making things a little bit more syntactically clean. I generally don't like these kind of packages because it forces the user to understand this package. I'd rather people just implement things in base Python than have like some specialty like Python syntax module that they then sprinkle all over the place, and then it makes their code harder to read. But that is just me. And then Boto 3, this is basically Amazon, so the ability to I think they were using it for storing. So this is where they're storing their models, right? I'm pretty sure using S3 is what we learned. Cool. So what else can we look at here? Let's look at the PRs. Who's PRing here? They have one branch. Pull requests. This is kind of cool. Sanchit Gandhi this is the guy who made the Whisper the Jack's Whisper. Oh, kind of cool. Look at that. So Hugging Face has its own config class, and this is basically making it a config class, or it's making the GPT config inherit from this pre-trained config class. That's kind of cool. I feel like I should start using this pattern from transformers, import pre-trained config, and then config pre-trained config. Okay, we got some more guys here from Hugging Face. This is a different guy from Hugging Face. We would need the open source model checkpoints, and then dot from pre-trained method should work with the checkpoints. Happy to help. Fucking thumbs up that. What other pull requests do they have here? Boilerplate MPS. Adds get device and renames clear CUDA cache to clear device cache. AMP is automatic mixed precision, so it's a form of training that allows you to use different data types. I think MPS is that the Apple chip? Boo, come here. Yeah, you wanna say hi to the stream? Come here, say hi to the stream. You wanna say something? Say something. Say meow. Meow meow meow. Okay. I'll let her die. So I think this backend MPS is basically just the Mac. Yeah. MPS enables high-performance training for GPUs on Mac OS devices with Metal Programming Framework. It introduces a new device to map machine learning computational graphs and primitives on highly efficient Metal Performance Shaders graph. Okay, so we have one pull request of the Hugging Face kind of squad trying to get this model into Hugging Face. We have another pull request, which is someone trying to add Mac hardware. We have this pull request, which is I like this. This is what we wanted, right? We wanted this at the so this is basically changing it from just a PyProject 2ML like that crap into a conda YAML and a requirements.txt. So actually I do like this one here. Let's give this guy a thumbs up. I like that. And what else do we got? Addition to help with the slow runtime of interpreting user audio. The fuck did they change here? no, this guy just added threads. This is weird. This is crap. This is like just very poorly written Python. Look at this. This is snake case with capital letters. And the doc string is above the function. The word parallel is misspelled. Here it has 2 R's and here it has 1 R. Here it has, what the fuck is this, dude? This is crap. "13-second bypass." What do we got here? More crap. Okay, so couple bullshit pull requests and then a couple good pull requests here. Cool. So I mean, that's largely what it is. That is Bark. It's an interesting audio model. I think it's quite good because it replaces 11 Labs. So up until now, I was using, for my audio projects, I was using 11 Labs, which is what I used for my speech-to-speech project. But 11 Labs is kind of annoying because you have to basically pay for it, right? You pay per token, and you have a limited amount of tokens. So actually, I can go here and like see how much I was paying for this, right? So now you finally have an open source and free alternative, so you can use this in your audio projects. The problem is it's going to be not via API. You're going to have to run this locally, although if they get integration into Hugging Face, you should be able to use it from Hugging Face, right? You could create a serving endpoint and then use it that way. But yeah, pretty cool. I like how they're basically what they're going to be trying to do, if I had to predict, is they're going to use the success of this demo in order to raise a bunch of money and then use that bunch of money to train a giant foundational audio model that is an encoder and a decoder, right? And they're going to use that in order to train their own version of Encodec, which is currently a Facebook model that has a commercial license or non-commercial license, so they're not allowed to sell anything yet. But yeah, pretty cool little demo, pretty cool little project. I like the emojis, I like the demos, and I wish the guys the best of luck. We got a couple different audio stuff this week. I think we got Language LM on Wednesday, and then I got a video on computer vision tomorrow. So if you guys are more interested in the computer vision world, not necessarily into audio and language stuff, I will be reading a paper on that tomorrow. So thanks for listening. Hope you guys have a beautiful week, and see you guys tomorrow.